Welcome to Spring LIB.
In this exercise, you're going to need the concept of cylindrical coordinates, so I'm briefly going to review it. Consider that we have Cartesian coordinates as shown here in the picture. So we have coordinates x, y, and z. And we have a certain point, represented by this green dot, that we want to represent in cylindrical coordinates. So what are the coordinates that we would associate with this point? Okay, so first we project the particle's position in the xy plane. Okay, so like this, I'm just projecting it, and in the xy plane we take the distance between the origin and the position of the projected position of the point in the xy plane, and we call it the coordinate r. Also, the angle that this line makes with the x-axis we call theta. Okay, so this is pretty much like the polar approach to coordinates, but this is 3D. And the last coordinate is just z, so we don't change it. Okay, so in the end we have a set of three coordinates, r, theta, and z, and these are our cylindrical coordinates. The position vector, which I'm going to call x vector of a particle, is given by r times the unit vector in the r direction, this vector here. Okay, this is the unit vector, plus z times the unit vector in the z direction, that is this vector here. The last vector, the last unit vector we need in order to have complete base is a vector in the theta direction, which is the vector that is perpendicular to both z and r. Okay, and is pointing in this direction here. This is the theta vector. Okay, it's still on the xy plane. Okay, and our goal, what we're going to need in this exercise, is to find what is the acceleration in cylindrical coordinates. So we know that the acceleration is the second derivative of the position with respect to time. And we can find that this second derivative is equal to, in the r direction, it's r2 points minus r theta point squared. Then in the theta direction we have r theta 2 points plus 2r point theta hat plus z point z hat. Okay, so now we are in a position to start our problem. This is the equation we're going to use. So what we have is a boy that is sliding down a spiral slide. So he has a mass of 40 kilograms. The radius of the spiral slide is equal to 1.5 meters. The theta angle of the boy is 0.7 times t. This is in radians. T is in second. And z, its position, vertical position, is equal to minus 0.5 t. And this is in meters. Okay, so what we need to calculate is what is the force, the components of the force, so Fr, F theta, and Fz, that are exerted on the boy by the slide at time t equals 2 seconds. So before anything else, I'm gonna just draw a force diagram on the boy. So here's the boy. Okay, there's a force, and of course there is the r coordinate, then the theta coordinate, and then the z coordinate. Okay. Okay. The forces that act on the boy are the gravitational force, that points downwards. So this is the gravitational force, mg. And we also have the normal that the slide exerts on the boy, which points somewhere like in this direction. Okay. Okay. So what I'm gonna need is to calculate the components of the normal. That's what the exercise tells us to do when t is equal to 2 seconds. So we have that the normal force can be decomposed into Fr in the r direction plus F theta in the theta direction plus Fz in the z direction. Okay. And we know that the normal minus mg in the z direction is equal to the mass times the acceleration, because mg, because the sum of the forces is equal to the mass times the acceleration according to Newton's second law. Okay, so what we have is Fr r plus F theta theta plus Fz minus mg is equal to the mass times the acceleration. Now we need to find what is the acceleration of the boy. So I'm just going to rewrite here the coordinates that we have. So we have that r is equal to 1.5 meters. Then we have theta is equal to 0.7 t radians. Then z is equal to minus 0.5 t meters. Okay. So the acceleration, as I said before, is equal to r theta to point plus 2r point theta point theta plus r to point minus r theta point squared r plus z point z. So we have that a is equal to 1.5 times theta to points. That's 0 because theta is 0.5 t. So actually, let me write this here. So we have the theta point is equal to 0, theta to points is equal to 0. I'm sorry, our point is equal to 0, theta to points is equal to 0. Our point is 0.7, r to point is 0, z point is minus 0.5, and z2 point is equal to 0. Okay, so we have 1.5 times theta to points at 0 plus 2 times r point, which is 0, times theta point, that's 0.7. So the first term here is 0. Then we have r to points, which is 0 minus r, that's 1.5, times 0.7 squared, plus 0. So in the end, all we have is that the acceleration is equal to minus 0.735 in the r direction. Okay, so this means that the force, so we have that Fr r hat plus F theta hat plus Fz minus mg z is equal to minus 0.735r. So we have that Fr, and actually minus 0.35r, this is the acceleration, and we have to multiply it by the mass, which is 40 kilograms. So we have that Fr is minus 0.735 times 40, which is minus 29.4 newtons. F theta is equal to 0, and F z is equal to 0 plus mg. which is 40 times 9.8 meters per second squared, and this is equal to 392 newtons. And this is our final answer.